So today's presentation for me will be about wound field synchronous motors, EESM, WRSM, however you want to call them. Basically a rotor with coils excited by DC current. And so for the story a little bit, I was studying at TU Darmstadt, and that was about 13 to 15 years ago. And I remember there was one presentation from Dr. Hackman, who is actually in the room today, which was already at that time talking about this development and how we can simulate these machines with different parameters and so on. So just to say that this technology is actually quite old. Lots of people have been working on it since then. I think since Continental actually took up the wound field synchronous motor, there weren't many developments in the automotive industry, at least not that I've seen. I mean, the first one made it into the Renault Zoe and some of the products from Renault. And now we've got a little bit of resurgence of this technology because BMW has decided to focus on it as well. And so they're considering their lineup to be now fully equipped with wound field synchronous motors. And this is why in the past couple of months, we've seen quite a few articles mentioning this technology. And so in this presentation, what we're doing is we're showing a little bit of a hands-on activity, how we can simulate this in JMAG and how we can get high fidelity efficiency maps with JMAG on this particular technology. The word high fidelity is particularly important because this is not an efficiency map that we would be using, for example, in one of the optimization routines where you need simulations to be done rather fast, maybe in a couple of seconds or a couple of minutes in order to get a large DOE. This is really to focus on the accuracy of the efficiency map and how we can generate efficiency maps of this particular motor with incorporating all the elements of losses. So this is really what this presentation is focusing on. It's providing a method within JMAG to do this and how to make sure that the efficiency maps we provide correlate very well to the final product that we will be then testing as a hardware on the test bench. So just a quick introduction to High Speed Limited. So we are one of the smaller companies here presenting. So this is why I would do a quick presentation of what we do. So we design, develop, and test electric motors for traction applications. We also test inverters. We develop inverters. This is our electric motors business. So we are a small team. So we're about 25 people. We're based in the UK. We were founded 2.5 years ago. And our main activities at the moment is to support OEMs in releasing machines in high volume production and supporting them through the design process and through the release process, but also supporting them with the manufacturing line development and how to manufacture machines in high volume. So we have facilities in the UK where we design, build and test electric motors. I won't stay on this too long because it's a bit boring topic, but we also do inverters. And we do hardware design from scratch. Our inverters at the moment are mainly bespoke inverters for our customers. We don't have any off-the-shelf products that we offer, and each of our inverters is tailored to whatever requirements our customers, mainly OEMs, require. And so at the moment, since 2.5 years, we've been developing a platform on which we can scale the voltages from 400 volt to 1200 volt using silicon carbide or IGBT power modules. And so this is one of our first inverters that is offered to one of our customers, and a product portfolio will follow, I think, in the next couple of years. One other highlight on High Speed Limited is that we have developed a continuous wave winding technology for electric machines, which is with a new set of, I would say, a new technology for manufacture, which enables us to use a stator core, so an inner stator core with closed slots around the teeth. So the continuous wave winding is rolled around an inner core, and then you have an outer core that is inserted onto the inner core, basically the yoke, to form the complete stator assembly. And this, we believe, has significant improvements compared to the standard process, where usually the continuous wave winding is rolled around a mandrel and then expanded into the teeth, which requires open slots topologies, and these open slot topologies usually have induced quite high losses in the rotors. And our first customer required a machine with a water jacket, and therefore we were trying to push the rotor losses onto the stator rather than having too many rotor losses, which would then require oil cooling. And so we came up with this technology in order to benefit from, first of all, the ease of manufacture, which is one step less than the conventional method, but also the improvement in performance and a slight improvement in efficiency, but most of all, the improvement in the reduction in rotor losses, which is very important. So even in permanent magnet motors where you don't have a field in the rotor. So the presentation today will focus on a WRSM design method, simulation method with JMAG, where we use this continuous wave winding topology. So this is a bit of a background in a comparison between EESM and permanent magnet synchronous reluctance. I'm sure everyone has seen a lot of this, and I think that it's a bit personal as well, how we take it. So, but I've tried my best to represent a like-for-like comparison between both technologies. And this is one motor that is based on, so the comparison is based on our permanent magnet synchronous reluctance motor, which is due to come into series production in 2024. And we have we keep more or less the same boundary conditions, whether it's electrical or mechanical. Of course, it cannot always be exactly the same, especially for the round field synchronous motor. We have a slip ring and brush assembly, which also takes some space. So it's difficult to do an exact comparison. But I would say, in general, the benefits of the WRSM that we do see, I mean, people talk a lot about efficiency and that the permanent magnet motor has a great efficiency. I would say maybe in terms of peak efficiency, the permanent magnet motor is very efficient. But if we do look at legislative drive cycles, we do see that weakening the field in the rotor does actually allow to be quite efficient over, for example, an EPA drive cycle or WLTP drive cycle, with the efficiency difference becoming quite minimum between the WRSM and the permanent magnet synchronous motor. Of course, the continuous performance, well, that I think everybody knows that for the EESM, we need to have an excitation in the coils, which induces losses in the rotor, which if we want a reasonable continuous performance compared to the permanent magnet motor, we will of course need oil cooling or whatever cooling we would use in the rotor. So those are mainly I would say, to summarize, that is our take on it. Here is a comparison of torque speed curves. So these are peak performance curves between two technologies, I mean, the EESM and the permanent magnet with similar boundary conditions. The major benefit we do see on the EESM, though, is that they have a very flat power profile, which is I think very well suited for traction applications, where usually the requirement is a flat power after base speed. So there are some benefits we have there. In terms of overload capability, the EESM is also has a benefit as well, where we can push quite a high current then through the rotor coils in order to create a very, very strong field in the rotor, also beneficial for peak torque, for example, below base speed. So this, I mean, we can discuss it. Again, this is our take. There are lots of different papers out there outlining the differences. So, but this is what we've seen in the past couple of years when we've designed, built, and tested these motors. And this is generally the outcome that we have seen. So this is, now we're looking a bit more into the process itself. So how do we calculate this efficiency map for EESM machines? So this is a short representation of how we do things. It all starts with a sweep of ID, IQ, IF, which, ID current, IQ current, and the field current, which of course can also be a phase advance angle amplitude of the current and field current amplitude. So we start with this. We then use that data to do an initial operating point search, where we search for the best possible combination of ID, IQ, IF, giving, for example, maximum efficiency. Or in this presentation, we focus on maximum efficiency, which is actually minimizing the losses. But you could actually choose anything, really. If you wanted to minimize the losses in the rotor, you would maybe have another combination of ID, IQ, IF. You can also do a weighting of the losses between the stator and the rotor to get another control table generating another efficiency map. So it has a lot of degrees of freedom, but the first part is really just to sweep the whole design space and to get back a CSV file where we obtain data that can then be post-processed in software like MATLAB or Python or Octave, whatever you're using. And two important parts after that process, post-process, is that we need to include an AC loss model. So the AC loss model is very important, especially at high speeds when you get higher frequencies. So this is something that has to be run in parallel. We usually do it with a couple of points, not many. So we don't run, for example, the AC loss at every single point in the efficiency map in order to get the AC loss. We rather run maybe 2 or 3 points dependent on speed with different currents to obtain a space where we fit the curves and obtain a function that you can then use to calculate the AC loss and the resistance increase factor for different speeds and different currents, and then embed it in the post-process. The other one is the PWM injection model. And this one, I just want to emphasize this a little bit because we cannot neglect the PWM induced losses in the motor. So even for the EESM, I know for the PSM, for example, in the magnets, it's very significant. And but even for the EESM in the iron core, it is something that if we want an accurate representation of the losses, especially at low loads where the modulation index is around 0.4 to 0.6, you will have a significant contribution of those PWM losses in that region, which cannot be neglected. So it can be okay for the first, I would say, design iterations where you maybe do an optimization routine and you try and find your best topology. But when it's really releasing an efficiency map, for example, to the vehicle teams in order to predict range and so on, this cannot be neglected. So we have these two real models that are run then in parallel after finding the operating points, and then all together mixed again into another post-processing where we then do a refined operating point search and generate the final efficiency map, which we would then call a high-fidelity efficiency map. So the first part is the IDIQIF sweep. So there's lots of text in here. So just to remember that when we create IDIQIF sweep, it is actually, we create lots of cases because the field current needs quite a high resolution in order for the optimizer after to find the correct combination of IDIQIF to drive like a maximum efficiency operating point. So in what we do in JMAG is that we use we don't create the cases one by one with the create cases table. We actually use the efficiency map generation model from which was actually designed to do the PMSM efficiency map calculations, but we adapt it to have so 4 parameters. The first one being the speed, the second one being the current, the third one being the phase advance angle, and the fourth one being the field current. So this allows us, for some reason, JMAG then creates these cases and modifies them much faster than if you did it with the create cases option. This is something that we've gone through with JMAG a couple of times to understand why that was the reason, but this is really our suggestion. So in a couple of seconds, you can really create about 1,000 cases if you really want to run something with a high fidelity, high density operating point. So this is the method that we use to create the cases. Usually, depending on how accurate we want it to be, it can be something anywhere between 500 and 1,500 cases, depending on how accurate we want the final efficiency map to be. So then we go to the initial operating point search. So we've assumed that we did the full sweep of IDIQIF. We have a huge CSV file with lots of parameters inside, torque, flux linkages, iron losses, and so on. And we will then use that CSV file in, so we use MATLAB, by the way, but our plan is to switch to Python in the future in order to not buy the MATLAB license. But I think Python, we've seen that it can be as good as MATLAB as long as we design and implement our own optimization routine. So for example, in MATLAB, we have the function fmin_con, which is quite powerful to search for a minimum. In Python, this is something that we would have to do ourselves. But in our opinion, the Python is very powerful in order to do that, and it would allow you to not have to buy the licenses for MATLAB in order to get this done. So we'll focus a bit on the initial operating point search. The WSM is quite tricky because when there is no field current, the motor acts a little bit like a synchronous reluctance motor. Whereas when you're at maximum field current, the motor acts more like a permanent magnet synchronous motor. So also one difference with the PSM is that we sweep the phase advance angle from -45 degrees to 90 degrees rather than from 0 degrees to 90 degrees, which gives you some interesting curves. So this here is a plot of the torque function of the phase advance angle for increasing currents. And you can see that if I apply a field current that is at its maximum, these curves become more like something of a PSM curve type. So when the optimizer has to find the optimum point, and the same applies for the voltage, by the way, the voltage waveforms are very, very different between the two use cases, whether we have IF0 or IF is Imax. And this is where it's very important to make sure the optimizer is programmed in a way to be able to differentiate between the cases. And we've had a lot of difficulties at the beginning with the optimizer finding the right point. So we had always efficiency maps pop up with a couple of points where data didn't make sense. So we ended up really scripting our own optimization routine rather than using something that was predefined in MATLAB, for example, the function fmin_con. So I think that's a very important point of processing the data with the WSM is try and find an algorithm that is suited to the WSM, which is kind of a mix between synchronous reluctance and permanent magnet type behavior, whether we're going from low field current or to high field current. So from the first extraction, we get the torque, we get the flux linkages, we get the iron losses in the stator and the rotor, and we find an operating point with an algorithm that is detailed here, but it's basically what I was explaining before. So we search for speed steps of 100 RPM. We try in torque steps of 5 Newton meters, we try and find the IDIQIF that minimizes the total losses under the constraints of the maximum line-to-line voltage and the maximum current. So one thing I didn't mention here is that we also run all our calculations in the slide before at 1 speed. So we use 1 speed and we use certain equations of the voltage to transform the voltage throughout the speeds, and we use a modified Steinmetz-Bertotti equation to calculate the iron losses for different speeds as well. So this is done at 1 speed, and the main reason for this is really for simulation time. We could run it at different speeds, but then it becomes quite unsustainable in terms of simulation time very fast. So the AC loss model. So there were a couple of presentations about AC loss, so I don't think I'll stay too long on this one. I think everybody knows that in a hairpin winding, of course, the conductor that is closer to the air gap has a lot more losses than the conductor that is close to the yoke, which is nearly DC. The way we include the AC losses in our models is that we take a couple of operating points that were defined in the first post-process. We take about maybe 3 speeds or 3 speeds and 3 different currents, 4 different currents, and we run these operating points like over 1 electrical cycle. And from those points, we determine the AC loss component, and we compare then the effective resistance to the DC resistance, which then generates curves for different loads, where we then define a resistance increase factor that actually represents the AC losses. So we don't run every single point. We rather create a function with a curve fit so that at the final post-processing stage, we can just use the curve fit and use the function and find our AC losses that were calculated in this model. So the last one, the PWM injection model, So this is the part where, at least from our experience, I think throughout the years working with the automotive OEMs, it is something we tend to neglect, and it's wrong. So these loss components that you see from the high frequency switching from the PWM generally really affect the behavior of the machine. So especially at lower loads. So if we want to reproduce a high fidelity efficiency map with accurate efficiencies at low loads, we cannot just rely on a sine wave injection for our loss computations. And this is valid, by the way, for the permanent magnet machine as well. So we've seen in the past that if you use a sine wave, for example, and you calculate the magnet losses with a 3D model, you get a couple of watts, maybe 5-6 watts. If you use this waveform, you'll maybe get 100 watts, 120 watts. So there is a real impact of using the PWM switching from the inverter on the losses of the machine. And this is something that cannot be neglected. So what we do in general is that from the map that we calculated at the beginning, we take one point where we believe that the PWM induced losses in the motor will be maximum. So it's kind of an arbitrary value we would take maybe for a modulation index at low load 0.5, where we expect it to be maximum, and run that point with a waveform that can be either generated from a PWM, an inverter model, or even within the JMAG circuit. This is something that you can also program. You can also use a measured waveform, but of course, if you don't have the machine at the beginning, you're not going to use a measured waveform. This is actually a measured waveform. So we've built this motor and we've measured the current. So what we're showing here is really a measured waveform. And we use this waveform implemented in JMAG, so as a time series. There's another way of doing it, which is just to take the waveform, do a Fourier decomposition of the current, and then implement it as a table of harmonics, which is also possible, which actually gave quite good results within JMAG. This one was sometimes a little bit unstable. But at the end of the day, what we're trying to do is to get the maximum PWM losses at that one point. Once we have those and we can separate the losses generated by the fundamental sine wave and the PWM component, then we can use analytical equations to fill in the entire design space and the full set of operating points. So here is one example of equations. There are quite a few papers out there that you can read which deal with this topic. So this is not one general equation. This is just the one we use. So we use the PWM max, which is calculated by injecting this current in one operating point, and use then the PWM losses will be function of the modulation index with a value of 3.14 and 2.47. So this is based on one paper that we're using. Of course, there are a lot of other models out there where we can do this. So this is the last part which we implement in the process. And once we have all the data, so if you start from the beginning, we have the flux linkages, we have the electromagnetic torque, we have the iron losses created by the fundamental harmonic, we have all the AC loss components. By the way, the AC loss components, we do extend them into 3D, but by means of analytical equations again. We're not going to create a 3D model to simulate this simply because it takes too much time. So we use that analytical equation to expand the AC losses into the end windings, which will be a lower proportion, of course, compared to what you have throughout the stack. We add the losses induced by the PWM switching, and then we process again with all these losses. And this is where really all the losses come into the equation. So in our case, we use slip rings and brushes. So we also have losses created by the slip rings, the brushes. We have friction losses, windage losses, and all this will then come into the last bit where we then do a final operating point search to generate the final efficiency map. And so this is basically what I was saying here. You can, to verify how exact the process is, we took some points to to put it back into perspective, to actually take what the post-process code gave us and run that operating point directly in JMAG. So here is an example of the magnetic flux density, stator iron losses, rotor iron losses. So the rotor iron loss density, of course, is very focused within the air gap region, which is always the case. And then from our perspective, what we have realized is that this process enables significant accuracy with the JMAG models in order to accurately predict the efficiency. So maybe it's not something that we would use to drive an optimization routine, like some of you were presenting yesterday. I think this would maybe be a bit too long. So I'll show you later, but it's about an hour, a bit more than an hour to simulate this. So maybe then if you were running 100,000 cases, I don't know, it wouldn't be very beneficial. But to release a final efficiency map, this is a process that we have developed over time, and we believe it gives reasonable results compared to whenever we test the motor, whether it's on a test bench or within the vehicle, and based on all the other losses around the drive unit that then give the range of the final vehicle. So here is an example of the outputs. I mean, this is just a snapshot, but you can see that generally what is interesting is that here, for example, the phase advance angle, you can see that the ISO lines are fairly constant. And this is really by optimizing the optimizer. So at the beginning, when we were developing this code, we were ending up with a bit wavy lines, so to say, not very accurate. It was diverging quite a bit from these kind of straight ISO lines you see here. But as we went forward and we developed our own code for the optimization routine, then we managed to get something that was reasonably stable every time when we ran the simulation, and generated quite accurate results, which we have then confirmed with testing. So a final overview of how long it takes us to generate this map. So the first one for the IDIQIF sweep, it takes us around 30 minutes. So we've got a license to have 2 cores on one job, and we run 2 jobs in parallel. So just to give you a bit of background on that time. The one thing that is very important is that we do not simulate one full electrical cycle. Actually, in theory, you would be able to only simulate 1/6 of the electrical cycle and reconstruct the remaining of the waveforms with that 1/6 electrical cycle. However, at the moment, we're using, in the iron loss calculation, we use the tools from JMAG, and we use the half symmetry for this routine. So at the moment, these 30 minutes are used with half an electrical cycle, but we're working towards using 1/6 of an electrical cycle, which would then reduce the time even more. So overall, for this map generation, it takes about 1 hour, which is reasonable. I believe we could have run the full sweep and the full map with all the points, all the speeds. I think that would have taken maybe 1 or 2 days to run. And with a combination of analytical tools and analytical functions and curve fitting, we managed to reduce this time to 1 hour for the round field synchronous motor. So that was, I think, the last slide. So if you have any questions.
Thank you for your presentation. I have one question. You mentioned that to calculate the PWM induced loss, you selected one point from the whole map, which you believe to be the maximum.
Yes.
How could you know that?
Well, usually, sorry. So you know that the PWM induced losses are usually maximum for a modulation index of around 0.5. Depending on the modulation that you use in the inverter. It depends also on the modulation you use in the inverter. But usually they are maximum around that value. Mm-hmm. So what we do is we pick a point where we use 0.5 modulation and calculate the losses from there, and then use a function to extrapolate them. So it is, in practice, I would say you may get a bit of divergence. I mean, you don't have it's not always 0.5, it's not always perfectly hyperbolic. It really depends on your inverter. But then you would start, in our opinion, especially with the PWM, you have lots of points per cycle. You would start simulating too many points to make it really time effective.
Does it make any difference if you select another point for this analytical expansion?
So we've realized that we did a comparison between a full map calculated with PWM and a map calculated with 1 point. And we looked at the energy consumption over the cycle, and we were within a 5% tolerance for it. So this is why we also decided to move forward with this single point rather than having 20 points. But I mean, you could think of maybe expanding it to 2 points or 3 points. If you have more cores than we do, because I mean, you were showing 160 or whatever, I don't know, then yeah, it's maybe something you could think of doing.
Okay, thank you.
Thank you for the nice presentation. I have a question regarding the implementation in JMAC. How did you modify the circuit to carry out the PWM simulation? Did you give it an initial condition for the current, or like a switch where you already have it the current steady state, or how did you implement it?
So you mean how we obtained the waveform, or?
No, the implementation directly in JMAC, how more or less a description of the circuit in JMAC.
So I say that again.
So did you simulate it directly in JMAC, the PWM implementation, or?
Well, we simulate the waveform. I mean, we use a PWM waveform that can be created either by taking it from a measurement, or can be created with the control circuit within the JMAC circuit. And we use that as a current source, so to say.
Okay, so you already give a current waveform to the model. You don't excite the JMAC model with a voltage source, but with a current waveform.
Yes. So we basically it's like running. I mean, we've got one. This corresponds to one IDIQ. So you've got one current amplitude, one phase advance angle, and you can actually see behind it is the fundamental, and overlaid is the current with the PWM, and we import it into the current source, and we just generate the 1 point.
Okay, so yeah, that was I missed that part. So basically, it was a current input, not a voltage input.
Yes.
Okay, and regarding the modulation mentioned 0.5, but I know one modulation index of 1 is for sine triangle. Is that what do you mean with 0.5? Is that sine triangle modulation, or
Sorry, say it again.
0.5 modulation index, would that be like sinusoidal as a sine triangle modulation, or 0.5?
No, well, I mean, it can be any. It doesn't really matter whether it's a third harmonic injection or a sine wave, or the modulation factor really is just the duty cycle of the pulses. It can be anything. I mean, it can be sine wave, as you say. It can be third harmonic injection. It can be 6-step, for example, as well. It depends. It can be any type of modulation strategy you're using.
Yeah. Okay.
So the modulation factor really is just the proportion of it represents the duty cycle of your PWM, whether you're using a third harmonic injection or whether you're using a
okay, you're referring to the duty cycle, not the ratio of the voltage. Let's say of the.
Well, it's linked. They're both linked.
Okay. Thank you.
But the modulation factor, I mean, it's a value, but as you say, usually linked to the ratio of the DC link voltage divided by the line-to-line voltage that you see.
Okay, I think we have one question here.
So thanks for the presentation. After computing the PWM losses, do you just update your efficiency number, or you recompute your current set points now to get the best efficiency with the additional PWM losses?
Yes. So what we do is that we we use the losses that were calculated when we ran the run with the fundamental. We calculate the losses that are used in here with the PWM, and we subtract them to find out the PWM-induced component of the losses. And then we save that like as a separate value. And in the final post-process, we add them all together in order to define the final operating point.
So do you find the optimum combinations again?
Yes.
So do you
yes,
see?
because it's slightly different. It's slightly different. It's not much different. I mean, you have only a few losses difference with, you know, I mean, you add the windage losses, the friction losses, PWM losses, the brush losses, and so on. So it's not a major difference, but it is a small difference in the IDO QAF. You won't end up with the same because you're adding additional losses. So when you do your loss minimization, you may find a different IDO QAF combination.
Okay.
Okay, so yeah, I know there is more question, but we're a bit running out of time. So we should go to the lunch break just after. So I suggest to continue the discussion during the lunch break. So if Cliff wants to stay a little bit, you can discuss with him here. And the other, you can go to the first floor. So it's restaurant, so the same place as the wine and cheese yesterday evening, not the same place as yesterday lunch. So thank you very much, Cliff, by the way, for the nice presentation.